150 megaparsecs, and the neural net is capable of looking at, of detecting it if the shear mass is high enough, etc. The way then in which we generate the images is by using PyCBC to generate basically the strain, both the plus and cross polarizations and the antenna factors. We combine these things and then we add it to noise. So for the noise, we've chosen to use unmodeled noise. So we take real patches of data in which the data quality was good enough and there was no event. Of O3A in this case, and we add it, we inject the signal into this noise to obtain the strain, and then we use the Q transform to have this two-dimensional image, this spectrogram, and then we use this normalization that you can see here. Basically, we subtract the mean, we divide by the square root of the variance, or the standard deviation, to normalize the data. And this is also very important. If we don't do that, the neural net is really not capable of training. So this normalization is a key point, even though it's very simple. Now we've generated of the order of 112,000 images, in which we've divided roughly 50% that contain a real signal, and the other one is the real noise that I was telling, so with no injection. And the neural net therefore has these two kind of images to be able to distinguish, so pure noise or noise containing a signal. And you can see here one of the injections that we've covered. This is a kind of low SNR, but you can still see the signal in LIGO and Hanford. Virgo is a little bit more blind to it, but still it adds contribution as in match filtering for detection, as you will see then. So for the architecture, we've chosen a convolutional neural network. This is being a topic in all the talks that we've done so far in GTNet. It's one of the best architectures that we can use in this case for pattern recognition. So it's a series of convolution and pooling layers, and after some of them, we just flatten the data and we go through some dense layers in order to produce a final number, which we call the discriminant. And it's a number kept between 0 and 1. In this case, we force this by using an activation function of the last layer to be a sigmoid, and this will represent how likely it is to contain a signal. So the closer to 1, the more likely it is to contain a signal. In the case of our neural net, we've chosen a ResNet 50, so I will not go into the details of the exact layers that it has. It's a standard architecture, so you can look for the exact layers. For example, I've given here a reference, but I'm sure that you can find in any place which are these exact layers. And the hyperparameters that we've used are this one, so a learning rate of 0.001. We've used batches of 32 images, and we've trained it during roughly 12 epochs. Between 10 and 12, it's already enough. And we've chosen an optimizer to be an Adam optimizer. It works well. We also tested some stochastic gradient descent, etc., but the Adam is the one that worked the best. And as a loss function, since it's a binary classification, we chose the well-known binary cross entropy. Now, we've trained a total of 7 convolutional neural networks, and we did that because we wanted to test the different inputs that we can really feed the neural net with. So we basically try to cover all possible interferometer combinations. So only training it with LIGO, only with Hanford, only with Virgo, then the double combinations and the triple one. Now, while we did that, we also tracked the 3 following metrics, basically the loss and the accuracy with the training set, just to make sure that it's really capable of training with the training set. And then we chose the validation accuracy as our way to decide which is the best epoch to keep. And you can see here on the left, one of the examples in this case is a triple combination, but more or less all of them follow the same tendency. So it trains correctly with the training set, and the validation more or less tries to follow the training procedure, but with these spikes and random noise, because sometimes it just fails to really learn it learns from the training set, but it does not apply well to the validation. And in this case, we just keep the epoch that has the greatest validation accuracy. Now, on the image on the right, what we can plot is the fraction of detected events as a function, so compared to the total number of injected events as a function of the network SNR. And as you can see, the best combination that we have is basically when we use the information from the 3 interferometers, as we would expect. And here there's also something that it's worth mentioning, and it's how do we say that we've detected something? We need to establish a threshold, because in the end, I was telling you that the neural net produces a number between 0 and 1, so we need to be sure that we establish a good threshold. And to do that, and this is how we've done that plot, is by computing the false alarm rate, as it's done also in the traditional match filtering pipelines. And we've basically set up a false alarm rate threshold of one event per year to claim that there is a detection. In our case, this was just to see how well it performed our neural net. And to compute this false alarm rate, what we did was basically time shift the data, as you can see here on the left. Basically, you take different interferometers, you shift a bit the data, and then you create these images in which if there is something, whatever it is, so any coincidence, it's caused by random, so by the randomness of noise, and therefore we are able to create a very large data set. In this case, we analyzed 152 years for O3A and 152 years for O3B. And that makes actually 10 to the 9 images. And this is why we had to use this GPU cluster that is held at Barcelona Supercomputing Center, because otherwise it was too much data to be analyzed in our own cluster. But thanks to that, we are able now to, according to the discriminant and the plot that you can see here, we can assign an equivalent false alarm rate. So how likely it is to be generated by pure noise. And thanks to that, we can now define this way of having triggers. And this is how we did the plot before. But also, another thing that we wanted to do is try to combine the results from different CNNs. Since we've trained 7 of them, we thought that maybe it was interesting to combine the results from different of them and, let's say, lower down the probability of having noise generated, or the triggering the neural nets. Because in the end, if there is an event, all of them should agree that there is an event there. If there is no event, there can be 1 or 2 of them just giving high confidence that there is something there due to a glitch, but the other neural nets should tell something like there is nothing there. So this is what basically triggered us to do an analysis of ways to combine the outputs. Now, we tried, first of all, 2 methods from the paper that you can see here. They also use CNNs to, in this case, identify eccentric, captures of black holes, and they also use these CNNs in spectrograms. So it was a great way to start because they've run into the same problem as we are. Now, the first method that they describe is basically by minimizing the variance of this function that would be the discriminant as a function of SNR, right? So they try to minimize these variance and say that they want the less possible variance in this function. And when we did that, in our case, applied to our particular case, so we're not saying that it doesn't work, it's just that for our particular case, it told us to ignore the triple combination. This is this beta 1 equal almost to 0. So that was bad for us. And I will come to this a little bit later, but that was very bad. We don't want to ignore the triple combination because we know that it's the most sensitive one. The second method, when we try to apply, so this is a little bit more complicated. It's basically trying to minimize the rejected events above threshold D0, which is computed as you can see here, and if not, you can go to the reference. But in our case, I will go fast because in our case, it basically the optimizer didn't converge because this function for us is not smooth enough. So with these 2 results, we were a little bit worried because we were getting nowhere. So we tried then to minimize the binary cross entropy. In the end, we want to classify. So we thought, okay, if we combine and we get a new discriminant, in the end, we should ask this discriminant to minimize again the binary cross entropy. So this is what we did. But in this case, the problem is that it's basically telling us to ignore 2 of the double combinations and basically only use the triple combination of and then the double that includes only LIGO. And this is also bad because, and this is why we have this plot here on the right, if we only use two neural nets, you can see here that the FAR drops very fast when you get to 1 or very close to 1. So really in this region of very, very high discriminant, you have a very steep gradient. of the FAR. And so it is very difficult to really assign an FAR in this region of the discriminant. Very, very difficult. Because even if you interpolate, the gradient is so steep that really it's almost meaningless. So it's very difficult to claim detections in this region. And this is why, in the end, we just chose to have the arithmetic mean, typical arithmetic mean, because at least it penalizes a lot when there is no events, so we have less false positives. And you have still like a lot of region here to really be able to detect. So as I was saying before, if you really have an event, you will be able to detect it because all of them will agree on that. But we are only using the arithmetic mean for the double combination, so 3 CNNs, and the triple one, 4 in total. We are ignoring the single ones because they have very low sensitivity, so in the end, they don't contribute much. And with that, we just can do an O3 scan. Basically, we can look for these kind of events in the entire data. And here is the typical plot of cumulative event count versus the inverse false alarm rate. And we've also plotted the expected background. And as you can see, there is no statistical confident deviation from the expected background. So basically, we are not seeing any kind of event. Everything is completely compatible with pure background as expected, because again, match filtering, all the searches that have been carried out have claimed no detection. So in our case, our results are just in agreement with whatever we might expect. Of course, we're covering a slightly different parameter space, but in the end, it would have been very weird to detect something while those traditional pipelines didn't detect anything. What we are now doing, though, is basically try to study the implications that our results have in the merger rate. Now, the way in which we are doing this is by computing the effective volume. As you can see here, is basically solving this integral over redshift, in which we have the moving volume, and what is most importantly here is the efficiency. This is what will change regarding our pipeline, our traditional pipelines and ours. And it's basically the fraction of events that you can recover at a given redshift. And we've marginalized over the rest of the parameters here. And when you have this effective volume, then you can recast it as a 90% confidence level upper limit, because we have detected no event. So you can use this basically loudest event statistic, in which it lets you basically recast this as an upper limit to the merger rate within this 90% confidence level. And on the right, you can see the comparison of our search in regards of other searches carried out before. For example, for the LIGO video collaboration in O3A, in this case, I've only plotted the PyCBC pipeline. They also use MBTA and GST-LAL, but I just took the PyCBC one because they are all of them very close. And I've also plotted the combined results from Alexander Neitz and colleagues from Hanover, in which they also use the data from O1, O2, and O3A. And as you can see, we're less sensitive. We expected this. Our method is not as robust as theirs, but we were faster, and we cover a little bit more of this parameter space. So we go to higher chip masses, and this is exactly what we were expecting. So this next step that we are planning now is to try to recast these merger rates as different limits to theoretical models of primordial black holes. So for example, since we are covering this mass range, we can assume theoretical models of PBH and astrophysical black holes mergers. We can also try to target PBH and a neutron star merger, for example, because we also cover these heavier mass that it's between 1 and 2, more or less, where neutron stars are expected to be. And we can also try the PBH-PBH merger, because we are also, some of the theories say that PBHs can have these high masses as well. So we can now, we are now trying to do physics with these results. And just as a conclusion, what we've shown here is that we have used a machine learning approach to detect these mass symmetric CBC events. We can do it, although unfortunately in the data there are none yet. Also, we have used this ResNet 50 architecture because it's basically very good for pattern recognition into the images, and it performs well here. We have also seen that this approach is less sensitive, and therefore these lower merger rates limits that we've placed. But they are way much faster. I haven't commented this, but the entire O3 scan in our case took an order of a day. So O3A and O3B together and you can compare to LVK. You know that takes of the order of months. So yes, we are not that sensitive, but we are going way much faster. So now it's only a problem of improving the efficiency of this neural net, but in terms of speed, this is amazing. We also explored a way to combine the outputs of the different CNNs. As I've told you, this FAR thing was a problem. So this was a way to improve the false alarm, so the false events that are detected by the CNNs. And finally, I've shown you also a way that we can use the CNN to do physics, so to recast these as upper limits to the merger rate. And now, well, the future plan is what I've said of recasting these as limits to different PBHs. And this is all from my side. If you have any question, I will be absolutely glad to answer it.
Thank you very much. I have one question, but maybe there are other questions from the audience or from remote. I see David's hand up. Okay. I don't know if let's try the microphone. Hopefully it will work. Can you hear me?
Yep.
Okay. First, I want to congratulate you. That number of noise files you do sounds really impressive. So 10 to the 9. I don't think I've seen anyone else push things just once to such a low false alarm level. That's really cool. And then I was wondering, for that training, so if I understood correctly, you use the real OSPA, OSPB data for the training. Do you then only use the time-shifted ones as a noise, or the real one as well?
So for the training, we use O3A data that is randomly placed, that contains no events, and that the data quality is good. So there are lots of ifs there. And then for the time shift, no, for the time shift, we use all O3 and we just shift it randomly by a factor. That is, so by a factor that there's no coincidence in any way, which was tricky at the beginning. But no, we don't use the time shifted for the training.
Okay, but so how do you really know there's no events in them before you've done the search?
Sorry, can you repeat that again?
You're saying where there are no events, but you haven't done the search yet. So the principles, couldn't there be exactly those signals that you look for in your noise training set?
Oh, yeah, so there could be, but in this case, since we knew when we did the training that the traditional pipelines had found none, so we just assumed that there are no events, and the ones that we skipped are the traditional CVCs. So we didn't want to inject our signal on top of a CVC that is known. We have the catalog, so we could some sort of neglect the periods in which the catalog that was already available, so the 2.1 catalog. So we could cancel out those times. And yes, we assume that there's no event because the traditional pipelines had already given out the results for O3A. So for O4, we should be a little bit more careful, of course.
Yeah, maybe you want to also time shift for the training set.
Sure.
Okay, fair enough. Thanks.
Other questions, comments? Not then maybe I will ask my question. This slide you have shown with the combining the information from different potentially weak learners. This sounds to me like ensemble learning or bugging procedure. Was that really what we did, or that was some sort of an ad hoc idea to try? Because there are this type of bugging or ensemble type of combining many different results that are each of them is weak, and at the end you may have something stronger.
Please. So this is one of the problems that now we are having because there's a lot of information and yeah, we need a statistical good way to combine it. So any other idea, we're just so very happy to try because it's.
Yeah, so if you didn't think about it, so there is a kind of a field of bugging, or this is called bugging or ensemble learning. This type of things may be useful.
Yeah, sure. We'll take a look at that. Thanks.
Because it looks like you did something kind of in this spirit, but I wasn't sure if that was exactly following this kind of rules or not.
I think some papers also call it committee.
Yeah, something like that. Yeah, so David is saying that it's called committee learning. Although you know what, they're also saying that things that are designed by committee are the worst, right? Okay. but okay, this actually may work because then you may kind of like propagate the different detecting kind of algorithms that are not very heavy. Each of them is kind of light, but then you combine the information at the end, and then maybe that for some cases it's actually better than to have one big detector. Okay. So that was just my small comment. Are there some comments from the remote side? I don't see anything, so we can move to the second talk of today. Thank you very much. That was very interesting. The second speaker of this session is Filip Morawski. So let us switch to quiz in person. So we have to patch his presentation and launch it on the and this laptop. Mask. Do I need to wear a mask?
Sorry?
Do I need to wear a mask when speaking?
I would say it's better if you keep it.
Okay.
So you need to save it. No? Mm-hmm.
Windows.
Yeah.
Somebody is calling.
So you know a lot of Spanish
I already
now?
learned, you know. That's the best, you know. So, is it this one? So,
Yes.
mówisz tak po prostu, tak? Bo tutaj tu są mikrofony w tym urządzeniu. A myślę, będziemy się czuć, to jest takie do przesłuchiwania. Okay, so ready to start.
Which microphone are you going to use?
Maybe, well,
You can attach this to your flow.
Really better. Okay, so can you hear me? Perfect. Okay. So let me start. So hello everyone, my name is Filip Morawski, and today I would like to tell you a few words about the research project I've been doing last year with Michał about searching for the phase transition in the dense matter equation of state using anomaly detection technique. So a long title, but very descriptive, as you're going to see in a moment. So as for the introduction, so the topic is about the phase transition, but in particular, it's about neutron star physics. For those of you who don't know what neutron stars are, or forgot, so it's one of those, let's say, end products of the star evolution. Yes.
We are not sharing the screen.
Oh.
Sorry.
Okay, sorry. Sorry, remote, we didn't share, but now we will share. Now it's haven't started.
Sorry.
Perfect. Okay. So, neutron stars, which are the end products of stellar evolution, so they are basically one of the most compact and dense objects, at least we are aware and capable of observing. So, because of those features, they are like a perfect candidate to be used as a kind of like extraterrestrial laboratory for extreme physics, because at the Earth we are unable to reach such high densities and pressures to study
let's say, potentially extreme phenomena that can occur in neutron stars. So among those, let's say, extreme phenomena are all sorts, for example, of phase transitions. So, for example, like the matter inside of neutron star at some point, for example, in the core, changing its phase from nucleonic or like hadronic or some strange matter, like quark matter. So we basically don't know what's there, but through the observations, either electromagnetic or gravitational wave ones, we might hope to actually learn something about what's happening inside. And yeah, this project is a kind of like an approach to do this, but from the, say, more data analysis point of view. So as I said, the neutron stars are associated with very high, say, pressures and densities, so they're very compact objects. And but we can say that those parameters, like pressures and densities, they're in fact kind of like microscopic in nature. And what we actually observe are more like macroscopic parameters, such as radius and mass. So how one can kind of convert macroscopic parameters that we can see into something that we don't see. So one of the approach to do so is to apply some sort of equations of stellar structure, like for example, Tolman-Oppenheimer-Volkoff equation. So here you need like a kind of model of the equation of state that describes how the matter changes inside the star. Like for example, pressure versus the star density. Then you kind of make the calculations, and at the end of the day, you can actually compute parameters, and then you can compare those macroscopic theoretical parameters into observations. And in this way, via, for example, some Bayesian inference, you can kind of get an idea of what might be underlying equation of state. Yes, so that's what I just said. And the problem with this method is that, well, obviously in reality, we always have some kind of measurement uncertainties. For some methods, they are larger, for some methods, they are smaller, but they are significantly impacting all sorts of analysis. And so in one of the projects with Michał in the past, we kind of tried to apply, for example, autoencoders to make an alternative to what I just said. So having some macroscopic parameters to reconstruct the equation of state, at least for some of those simpler equations of state. And it worked quite well also for the some let's say kind of data with some measurement uncertainties as well. So a few words about how the actually, let's say, masses and radius, those macroscopic parameters are computed, because we cannot take a ruler and measure a star radius. It's too far away. So this is also kind of like a model dependent analysis. So there will always be a certain uncertainty of one can measure. And an example of an experiment that's used to actually tell us something about the neutron stars is NICER, so Neutron Star Interior Composition Explorer. If I'm correct, that's just kind of like a device, kind of like a satellite connected to the International Space Station, if I remember correctly. Yeah, so it's a kind of like X-ray timing and spectroscopy instrument focusing on rotation-powered millisecond pulse range. And why is that? Because neutron stars, beside the fact that they are like super compact and dense, they often have strong magnetic fields. Often the axis, like the magnetic axis, is misaligned with respect to the rotational axis. So when we observe a star, we can see certain pulses associated with regions of some hot areas at the surface of the star. Because as a consequence of very strong magnetic fields, like the particles, which are kind of like attracted to the poles, are kind of like heating up the surface. And the temperature that those areas reach are like of millions of kelvins. So they are very strong sources of X-ray radiation. And that's what we can actually see when the star is rotating with this misalignment. Those kind of pulses appearing in some periodic manner. So that's what we observe. Of increased and decreased radiation, and we can use it and some kind of profile modeling. So it's like a similar technique to mass filtering that you assume certain template of what's the star, like mass, radius, and so on, and via some inference analysis and likelihood calculation, so on and so on, we can, at the end of the day, have a notion of mass and radius. And obviously, like the values of mass and radius will also depend on the precision of this initial like data acquisition. Nevertheless, some uncertainties will be here. So a note about, for example, NICER, that it has already been used in concatenation with the gravitational wave analysis, for example, this merger of binary neutron star system a couple of years ago, to kind of help to limit the potential like boundaries for the equation of state in terms of the parameters that might be there in the star. So I just wanted to mention this because that's one of these earliest examples of this multi-messenger astronomy in terms of learning something about neutron stars. Okay, so that's basically it when it comes to neutron stars and this introduction. So what exactly we wanted to do is to search for the phase transition presence using neutron star observables such as masses and radii. And to do so, we decided to follow anomaly detection approach based on normalizing flows algorithm that I'm gonna cover in a moment. And the idea here was to, let's say, bias a model toward a particular type of data. For example, train the model on the data that contained only kind of like observations without phase transition, the underlying equations of state without phase transition, and to test it on some things that were, let's say, anomalous in that context. So they were just different from the training, totally different from the training data set. So what exactly are normalizing flows? So they are artificial neural networks, and they are generative algorithms similar to generative adversarial networks or variational autoencoders. And they can be used in, let's say, two ways. So first and foremost, that's an algorithm that allows you to convert, let's say, a complex distribution describing your input data into simpler form. Ideally, in the to the form of, if I'm correct, n invariant Gaussian distributions. And the n refers, it is latent, the representation refers to the dimensionality of the data, of your input data, of your number of features. So it's not a type of algorithm that actually reduces, let's say, the size of your data. That's not what it does. It's instead just converts one representation into the other, and you can later on use this simplified representation in the latent form to recreate samples in this generative way. However, in this particular project, we are not interested in the generative nature of the algorithm. Instead, we just wanted to focus on this latent representation, because the idea here was the following. Since we expected that if the method works, you would have like those n invariant Gaussian distributions. So if there is like an anomalous event at the input, so something totally different from what's known to the model, then the idea here was to, or the way it would work would be to kind of reflect this new input data anomalous event in the tails of the distribution, because that would be quite, let's say, the probability of such an event would be quite small. And since those distributions would be like Gaussian, we could run all sorts of statistical tests and so on. Like it's quite easy to work with Gaussian representation. So yeah, we could use basically those latent representations with samples either around the peak or either in the tails to define certain metric and say that, yeah, okay, for a given, for example, false positive rate, we are able to detect this and that like samples as anomalous. So the data we used, as I said, were of two kinds. So equations of state with phase transition or without phase transition for the training. And to simplify analysis, for the training, in particular for the training stage, we used as a models of equation of state relativistic polytopes. They are quite simple mathematical models, usually used in this sort of studies, that allow you to create quite large or cover quite large parametric space of equation of state. That still resembles some certain, let's say, astrophysical features of the stuff. And as for the test, we also use at least partially relativistic polytopes. However, as you are going to see in a moment, in this case, they were a bit different. And we also used one astrophysical model, like an extreme model of Drago from 2014, just to test like what would be the response of our method towards this very peculiar equation of state and what kind of observables one can have using it. Yeah, so that's basically the relativistic polytrope as for the equation of state. So you can like concatenate a couple of those relativistic polytropes and create quite, not really, but quite well cover this potential parametric space of pressures and densities. And once you have those models, some equations of state, you run T of the equations, and you have those theoretical mass radius relations. So on the left hand, you can on the left plot, you can see examples of those relations for the no phase transition case of the training data sets. On the right hand side, on the right plot, you can see cases with phase transition. So as you can see, they are quite different from each other. However, the thing the feature that kind of connects all of them is that all those models have separate branches and describing the, let's say, the stars, at least in this representation, so master radius. And the red one, so EOS1, is the Drago model. As you can see, it's the most distinct in terms of branches. So yeah, that was one could also say the easiest to analyze. But at the same time, we're curious what would be the response of our method toward this type of equation with respect to all the others. Yeah, and we also wanted to include some realistic neutron star mass distribution, because at the end of the day, those were just theoretical relations. We still had to sample an actual observations. So yeah, we use this double Gaussian distribution that seems to follow the distribution of masses of neutron stars, at least in our galaxy. In reality, we don't really know what's the neutron star mass distribution, but that's a good guess. And we also added some measurement uncertainties drawn from the uniform distribution. So at the end of the day, from those, say, theoretical relations, you have an actual virus resemble what's actually happening, what might actually happen in reality. Does it work, or?
Maybe the battery is there.
Yeah, I think it's the battery, but I think you can use this one.
Okay.
Yesterday we had the same problem with this mouse, and it was like battery. Sorry.
Okay, works perfect. So basically, that's it when it comes to like the data generation procedure. So now time for some results. And the analysis in this particular project consisted of a few steps. So first and foremost, we had to check the latent representation, because as I said, that would be the key part of the analysis, to actually see that there are some differences between anomalous events and non-anomalous events, and indeed they were. So here are, let's see, two cases studied in the project. So data without any measurement uncertainties. So let's say ideal kind of observations, and those with largest uncertainties of considered. So those bottom plots. And left columns resemble latent representations. So all those Gaussian and Gaussian distributions. And yeah, without phase transition, so data kind of like known from the training. And in case with the front phase transition present. So as you can see, in particular for the case without measurement uncertainties, the differences are obvious. So one could easily say that, yeah, there is something really going on here, because those representations are totally different from this. And once you start adding kind of like some random noise to the data, then obviously those differences are becoming, let's say, less and less significant, because both representations start to resemble just something noisy, something of similar nature. Nevertheless, at least in some cases, this phase transition, for the phase transition data, there were some off things, at least at the case of this distribution. So it seemed that our method kind of works, and that we are curious from the quantitative point of view, what are actually the results. So instead of working on those like n-dimensional representations, we decided to use some metric. Since those were Gaussian distributions, you could use all sorts of probability, for example, but in this case, we decided to use Euclidean distance, computed with respect to those, say, centers of the coordinate system in this multidimensional space, because it seemed to be good enough and quite easy to compute. And yeah, and the first step concerned comparison between the distributions, in this case, of those Euclidean distances. First and foremost, for the cases without phase transition, so something, let's say, from the training, which is this grayish histogram, and all the other equations of state. And that's also the reason why we chose only 6 equations of state, because here we wanted to study in more details each and every equation of state, or rather the response of the model towards it. So as you can see here, yeah, basically in all the cases, the differences are quite substantial with respect to this like gray histogram. And as for this EOS1, so the most extreme case is basically this like histogram, which is kind of like super far away in terms of this like parametric space of Euclidean distances. So that would be really like a safe guess if that would be, let's say, reality. So having observations resembling this equation of state, you could easily see it as an, let's say, anomalous event. And interestingly, even with some uncertainties, still this equation of state was quite easily differentiated from all the other samples. So in all the other cases, well, it wasn't as good, but still, yeah, this particular behavior was perfectly fine, because that's what one can expect once you start adding uncertainties, especially if they're like large ones. So having those histograms and seeing that at least partially they overlap, we could compute ROC curves. That's what you can see here. And yeah, as expected, for example, in terms of area under curve, once you start adding larger and larger uncertainties, overall the ROC curve and this area under curve parameter will become like lower, lower, and lower. So that was perfect, because it confirmed that this method works in kind of a predictable way. And yeah, we also kind of studied in this project, say, 3 different number of observations, because we are curious if, for example, by increasing number of observations, we could, in principle, improve, for example, AUC for a given, let's say, uncertainty study. And indeed, that was the case, because as you can see, even though like we increased the uncertainty, so this is like the smallest, it's like around 1% of the initial values error, it's 5%, 10%. Once you increase number of observations, those numbers improve. So that's great, because again, that was another confirmation of predictability of the method. And the last stage of this project concerned the studies of the detection efficiency, because if you have like this ROC curve, you can easily set false positive rate at a particular value, and FPR will correspond to certain value in this particular case of the metric. So in this particular case, Euclidean distance, and everything above it will be considered as anomalous event, under assumption of a given percentage for FPR. So yeah, like there are a lot of numbers here, but yeah, the most important conclusions are that Yeah, so EOS one, so this like extreme case in all of the studied configurations were easily detected as an anomalous event. And for the other cases, by changing, for example, number of observations for given uncertainties, we could also like increase the detection efficiency. So the methods seem to be like, have like some predictable character and yeah, kind of work, because that's exactly what we hoped at the end of the day to have. So that's just like a brief summary of what I just said. So yeah, I believe that this approach, like, in general, like detecting anomaly, has interesting future because there are like newer and newer algorithms introduced capable of doing this. And yeah, what I like about the anomaly detection in general is that you really focus on certain aspects of your data. So you're like biasing your model in particular way and focus on kind of like detecting like everything that's different. Whereas in classification, often you just try to learn features over the certain signals, for example, which is not the case here. And yeah, I highly recommend it. I highly recommend trying this approach for your own projects, because it's really fun in general. So thank you.
Thank you. We have some time for questions or comments. Are there some? Okay. Yes.
So have you tried to apply this, or are you planning to applying this to real data? Because I mean, there are data already from NICE, you have the gravitational wave data, the X-ray masters. I mean,
So-
there is some data.
I know.
So you could apply it directly.
In principle, yes. So I guess with Michał, first we wanted to expand this toward the gravitational wave data. So for example, chirp masses and tidal deformabilities to see if it's like behaves similarly. It should, but yeah, like that would be like the first step, because then you could, for example, concatenate both approaches, like gravitational wave ones and electromagnetic, in the context of multi-messenger astronomy. And then yes, at some point, like testing actual data would be like a nice trial to actually see if there is, anything interesting.
Yeah, that would be very interesting. Thank you.
Thank you.
I wanted to comment on that because you probably have noticed that in this talk, Philip didn't mention gravitational waves.
I did.
Just a little bit, right? But these results are not about that. But indeed, yes, the same, because gravitational waves, we don't measure radii, we measure tidal deformability, something like radius, but not exactly, something slightly different. So in principle, one could think about masses of the binary or chirp masses and the tidal deformability. Now we measure something, or at least estimate something that is tidal kind of sum of tidal deformabilities, kind of weighted sum, this famous lambda tilde, which is something like a radius kind of the binary. So in principle, that is an input, and in principle could be used in the same way. So we are thinking about trying that because, of course, the errors of lambdas are much larger, although the errors of chirp masses are much smaller, which is kind of an interesting situation. So gravitational waves can give us something else.
Thank you, very nice talk. My question is also about the data, but also about the model. So there is a connection between data and model. Can you tell a bit more about what do you mean by phase transitions and how do you generate the data?
But phase transition, it's like as the name suggests, like the phase transition, like water becoming the ice, but in case of neutron stars,
you can concrete in the model. How do you define formally, mathematically? How do you define?
So as I said, at least for the relativistic polytropes, like here, there is no information about let's say, the astrophysics. Because what you are just trying to connect or disconnect in terms of phase transitions, for example, you have just like this non-linearity somewhere, like a jump. Yeah, the discontinuation.
Like second order phases.
Exactly. So that's
yeah. First order transitions.
Because I think in this graph, I think this is second order.
Here, there's something like a second order or maybe mixed phases, but he was actually showing examples. There's this this one. Yeah. So here you can see that. I mean, you cannot see it here, but if you integrate the Tolman-Oppenheimer-Volkov equation with an equation of state with a phase transition that is the first kind, first order with a huge jump, then you will get some sort of a discontinuity in this mass.
Yeah, they're just separate branches.
And this part of the branch, there is a unstable part here that is non-existing because it's unstable physically, and that's why we call it separate branches, because we assume that we expect that this part will not exist in reality. Right? So and this is the smoking gun of this type of phase transition, but kind of in this macroscopic point of view, because we have no access, we have no direct access to the microscopic equation of state. We also don't have direct access to this because when we observe, we are astronomers. But at least we can detect them, the masses in different points and radii, and then from that infer the existence of this microscopic behavior. So it's slightly convoluted, but not impossible. But we can continue this discussion about phase transition because it's we actually don't know whether it exists. We don't know what order it has if it exists.
And what does it refer to either?
So there is a lot of question marks here. It may be that there is no phase transition in dense matter. Also, yeah. But usually we think that there is at some densities much larger than the density of atomic nucleus. There is a phase transition from hadrons, protons, neutrons, and so on, to the deconfined quark matter. So quarks are falling out of the neutrons and protons and flying around freely like a Fermi gas.
Okay. And have you analyzed the effects of this gamma in the model? You have a parameter gamma, and is it somehow visible? How does it affect?
So this
Yes.
Okay, and this gamma is the same gamma as in the next picture, right?
Yeah.
Yes.
Okay,
we call it stiffness. It's like whether this behavior pressure density is kind of goes steeper or less steep. If it goes less steep, you call it soft, because you can increase in density but not increase in pressure. If it's so, it tells you a little bit about the state of matter in terms of how likely it is to be squeezed. This type of thing. We call it this is called adiabatic index because it's kind of related.
Okay, thank you very much.
Okay, we are perfect on the time.
Are there any questions like remote or?
Yeah, is there
here we can continue at the coffee break, but I don't know, like remote might be.
On a remote coffee break, perhaps.
Remote questions? If not, like, I don't know. Would we see anything?
I think we should see. A voice from.
We should. Voice from the sky. Good.
I don't hear anything, so we can.
I guess not.
Thank you very much
for
the talk. And then we are moving to the third talk today. Please yes. I didn't know. We are remotely. All right. So, but wait, I have to upload your talk.
Let's try. You can click these two. Sorry.
Now I don't know how to do the sharing.
one. There.
Shall I click this?
True. Should I just use the other one?
Yeah.
Yeah.
Okay. This is if you need it, and then back and forth.
Yeah. This section?
No.
No.
There is a little.
Okay.
Okay. Okay. So we move on. Can you check if this is sharing to the?
Yeah, sharing.
Okay.
Okay, so I'm Lee from the University of Glasgow, and I'm going to talk about a project me and, well, a lot of my collaborators as well have been working on applying Gaussian mixture modeling to the short all-sky burst search. So to start off, I'll just give a quick overview of the search itself. Burst events are defined as gravitational wave transients with generic unmodeled morphologies, and for the all-sky short search specifically, these are short duration transients with times ranging from a few milliseconds to a few seconds, and they also have a frequency band of 24 to 4096 hertz. So the all-sky short searches for both generic waveform morphologies from unknown sources, as well as astrophysically motivated waveforms such as supernovae and pulsar glitches. And the main thing to know about this is that they can't be detected through your usual modeled search algorithms such as match filtering. So instead we have to use unmodeled searches such as coherent wave burst and phase wave as well. But we're only going to talk about coherent wave burst for this work. So as I said, it's unmodeled. It doesn't require any prior knowledge on signal morphology, time of arrival, sky direction, or polarization. And it instead uses excess coherent energy in the time frequency domain across the network of detectors. I've just put in an example of a frequency time map to demonstrate this a bit. The signals down here, it's actually a double blip waveform, which is why there's two peaks, but it's just to demonstrate what the time frequency map looks like. So it combines data from multiple detectors to create coherent analysis, and the background is estimated by applying an unphysical time shift. The main problem with this search is that noise glitches are hard to distinguish from signals. This is especially the case for blip glitches because they have a short duration and often low quality factor, which is the same morphology as the signals targeted in this search. So this is one of the things we wanted to improve by applying Gaussian mixture modeling, as well as just the detection efficiency in general. So a bit more specific information about coherent wave burst. For the standard all-sky search, it's done in a low frequency part and a high frequency part. This work only looks at the low frequency part. This splits the data into 3 bins to improve the detection efficiency. This plot is actually from the first observing run. Here's an example to demonstrate how it improves the detection. So the first bin is normally the noisiest one. It's seen as the solid red line in this plot. And as you can see, it's got a much higher limit on false alarm rate than the other 2 bins. So if the bins weren't there, all the data would be limited at the same level as this solid red line. For O3 search specifically, the 3 bins are, well, the noisy bin contains signals with energy confined mostly to one oscillation and quality factor low 3, which is the bin where most glitches fall into. That's why it's the noisiest. And then second bin is all other waveforms with lower quality factor, and the third is just high quality factor waveforms. Because of the bins, the IFR is penalised by a trials factor of 3. but the benefits outweighed by the improvement in detection efficiency. Oh, it's also worth noting that the low quality factor corresponds to wide frequency bandwidth, and high quality factor is narrow frequency bandwidth. So these are the attributes that describe the data. It's not too important for you to know exactly what's going on here. I just wanted to introduce them because they're used in the analysis later. So frequency, duration, SNR, I assume everyone knows what they are. And then we've got two coefficients that describe the network correlation. There's a few to do with energy in the middle, ratios of reconstructed energy, coherent energy, residual noise, and then the gw attributes describe the morphology of the waveform. We have quality factor, which was mentioned earlier, and gw0 describes the energy distribution over different time segments. So these two are what separates data into bins. And then the last three L-betas are all to do with the localization of the tree in the time frequency map. So just a quick overview of the process. The data goes through time frequency transform, and after data conditioning, it goes through pixel selection through a selection rule based on a specific energy threshold. In general, the most energetic pixels are singled out as the core, and then the surrounding pixels are counted as a halo. And then you go on to cluster Ds, and they go through another selection rule before you calculate likelihood and other detection statistics I just mentioned. The main thing to note here is that we apply the Gaussian mixture model at the post-production stage. So after the computation of detection statistics, but before the data goes into the binning. Okay, so to get on to Gaussian mixture modeling, it's a probabilistic model which uses unimodal Gaussian distributions to represent the multimodal dataset. When this allows for subpopulations to be identified in data and models as a superposition of Gaussians. This is just an example to show you how it works. This is just a randomly generated data set. And you can see that there's structures in the data that can be modeled separately, so the Gaussians fit to them, as shown in the plot here. So if we say a data set has D attributes, then it can be modeled by GMM as a superposition of K Gaussians as shown here. Where the Gaussian distribution itself relies on, it's described by a d-dimensional mean and a d by d covariance matrix, and we also have the weight on each Gaussian in there as well. Now these parameters can be estimated by maximizing the individual log likelihood, except this can't be done analytically. So we use the expectation maximization technique, which is an iterative algorithm that converges on the maximized likelihood and gives us the estimates to the parameters. But we have another problem with this, is that it can't predict the optimal number of Gaussians that we need to fit to our data set. So we introduced the Bayesian information criterion for this, also known as the BIP. So for a range of number of Gaussian components, we calculate bit values, and then the lowest bit value will give us the optimal number of Gaussian components that we need to fit to our data. And that's just an example of bit values for the number of Gaussian components. You can see the minimum is somewhere around here. So once we have our optimal parameters, we calculate the maximum log likelihood. Noise and signals are distinguished as two separate models. So for the background and signal simulation data sets separately, we can calculate a detection statistic for each trigger. where we take the maximum log likelihood based on the signal and take away the maximum log likelihood based on the noise. An example of this is for the O3 data here, just to show there's a clear separation between the signal, which is there's a range of simulated injections to the right here, and then the noise is like separated from it in the blue to the left-hand side. So we wanted to apply this to CWB to improve overall detection efficiency and mitigate the effect of blip glitches. As I said, we did this at the production stage, which means there's no need to separate into bins, and this removes the need to penalise IFR with trial factor. We use 11 of the attributes that I described earlier. Frequency and duration are involved because they're a function of the injected population. We don't want to introduce a bias. We also reparameterize these with log and inverse sigmoid functions, and we introduce a new parameter, which is a ratio of LV01 and LV0. This just makes the Gaussians more well behaved. So this work was done by Dixie and Lopez. There's a paper out in the archive on it. There's another link to it at the end. But we consider triggers with SNR over 5.5 and cross-correlation coefficient over 0.5 in the HL network. We only use the HL network because it's most sensitive for this work. They're co-aligned, so they're sensitive to similar polarizations. These are the simulated injections that we used for training our model. We have a range of different sine Gaussians, white noise bursts, and Gaussian pulses. These are standard to the O3 all-sky short search. So we randomly split up the data into 3 sets. 10% for validation is what we use to calculate the BIC and the number of Gaussian components needed. And then we take 70% for training the Gaussian mixture model itself. And the remaining 20% is for testing. And it's worth noting there's an equal distribution of injected waveforms over all the different data sets. Originally, we had approximately 1,000 years of background data, but obviously it goes down to 200 years due to other data being used for training. Okay, so now we're on to the results. I have some ROC curves here. Detection efficiency is calculated based on the T statistic described earlier. The best improvement here is on Gaussian pulses. You can see it's quite a big jump from around 0.3 to 0.6. Since these waveforms often fall into the noisy bin containing the blip glitches, that's why there's such a big improvement. So we can conclude that GMM mitigates the effect of blip glitches. I should have said, the solid lines are the GMM plus CWB algorithm, whereas the dotted lines are CWB alone. So the Gaussian pulses have an overall improvement of around 125 times in sensitive volume. I can go on, there's a lot of plots here. For the sine Gaussian and white noise bursts, they pretty much all show the same. There's a slight improvement, not as big as the Gaussian pulse, and a typical improvement of around 1.33 times in the sensitive volume. It's worth noting here that the improvement could be attributed to the removal of the trial factor as well, to some degree. So we also tested it on some core flat supernovae waveforms. These weren't included in the training set, so it's a good test of robustness over a variety of waveform morphologies. you can see there isn't as much improvement here as the other waveforms. The largest improvement is seen in the M39 type supernovae at low FAR, sorry. And the rest of the models have either comparative efficiency or a slight improvement. These are the results for the standard O3A data. We have the cumulative number of recovered events for CWB alone in green, and then CWB plus GMM in purple for a range of IFAR values. The main thing to note here is that we recovered all the CBC events identified by the targeted CWB search. There's a higher significance for some events, and if you look at the dots on the left-hand side, these are the results when there's no known CBC, and the grey line behind is predicted background, and we reached that within around 1 sigma. We're less sensitive to low mass binary black hole systems. This needs investigated a bit more, but we think it's maybe due to the injected signals used, because these sometimes have longer durations than the typical injections that we've used. So to summarize, CWB plus GMM enhances the detection performance for generic morphologies. Typical improvement of 1.33 times in sensitive volume, about 125 for Gaussian pulses. Assists classification of blip glitches, and the improvement in collapse supernova injections demonstrates the robustness of this method across different morphologies. We're currently doing work on this in hope that we can use it for the O4 run. And yeah, we've got papers down here. The first one describes the general methods of applying Gaussian mixture modeling to CWB in more detail, and then the application and results for the O3A search is in the second one. Thank you. Any questions?
Questions? Okay.
Hi. So I think I was distracted at the beginning of the talk, and maybe I should have downloaded the slides before. But so there is something that I've not understood. So the output of the Gaussian, the GMM, is that at the end you have a reconstructed waveform. That's what you have. So you improve the reconstruction of not the waveform, of the output that you are, or I misunderstood everything.
So, I'm sorry, I might have misunderstood your question, but so we calculate the detection statistic, and this helps with distinguishing whether it is a signal or a noise event, and then from that we I guess you do extract away from, in some sense, you detect the various signals. Is that what you mean? Yeah.
I think that your question is more about also, I don't know, it was like that, but because you asked about the waveform, but the work is not on the waveform, but on outputs that are not waveform parameters. There are some other parameters produced by CWB, right? That was kind of the question. And then the morphology of distribution is different for signals and different for other things, basically, and you study that.
Yeah.
Okay. Other comments, questions? By the way, this presentation is also on the website, so if you missed something, have a look at it later.
I think you mentioned early on that the expectation maximization algorithm, you can get the number of components out of it. I think there is a method for it we can discuss on a copy later. I remember having used some obscure thing.
Okay, yeah, that'd be good. we were finding that there was a lot of overfitting. So that's, yeah.
Okay, last comments or questions before the coffee break? Yes, okay. We do the round 3. Yeah.
Hi, thank you for your talk. It was very interesting. I was wondering if you guys have planned on applying this type of methodology to other pipelines, like other type of streamers.
It's not being talked about currently, but I don't see any reason why it couldn't be applied to other pipelines. We're still like finessing it, I guess. Like there's still some work to be done to like investigations to make sure we know what's going on in the results. So after that's done, then yeah, I'd say it's feasible to extend it to other pipelines.
Okay, thank you very much. I think there are no other comments or questions. Let's stop the session for now and have some coffee. Thank you. Thanks.
Thank you very much. Thank you very much to everyone this morning. I think it's wonderful we don't have too many technical problems. So we are going now to have a coffee break of half an hour. So everyone connected online, take your coffee, go to the kitchen of your home or office and take your coffee. And we will be back in half an hour.
So we start at 11:30, right?
Yeah, exactly, 11:30. Yeah, it's like 11:30. And for people here, just follow me and I will show you. Ahora probaremos a ver si funciona.
No funciona. A la fila, pero no.
No, pues entonces ahora bajo y se lo pregunto a María Ángeles. ¿Bajas tú con ellos a la junta?
A la que va juntas.
A la junta, luego se ¿vale?